today we're going to be talking to you about Euler's identity and its use with complex numbers.
So the first thing we're going to look at is imaginary numbers. So when you square a positive number, like 1 for example, you come out with another positive number. So every time you square a positive number, you get another positive coming out. And when you square a negative number, like -1, you come out with a positive number. So you can say that every time you square a negative number, you'll always come out with a positive. So the square root of 1 is 1 or -1. But what can you square to get a negative number? Or what is the square root of a negative number? Well, in this case, we call it I, which is the imaginary unit. Now, in the same way that we count our real numbers, 1, 2, 3, 4, 5, we can call them 1, 2 times 1, 3 times 1, and so on. We just replace the 1s with i's, so it's I, 2i, 3i, and so on and so forth.
So complex numbers are what we get when we mix these imaginary numbers with our real numbers. So if we took a real number and an imaginary number, and then we decided to add them together, we'd get a complex number, which we represent with the letter Z. This is called the Cartesian form of representing complex numbers, and in general we say that Z equals x plus iy, where x is our real part and iy is our imaginary part.
Now, we might want to represent these. Like, you would represent the normal part on like a number line, so we can still do that, so we do that like this, the 3. But we need somewhere else to put our 4i, because it can't be on the same number line, so we add an extra axis. We can then mark a point where these two are, and draw a line to the middle of the graph, called the origin. The length of this line we call r. We can also mark the angle between this line and the axes with the number line. And we call this angle theta, which is a Greek letter we use to represent an angle. And this diagram is called an Argand diagram, or a complex plane.
Leonhard Euler was a mathematician in the 18th century. He was born in Switzerland in 1707, spent most of his adult life living in Germany. He wasn't just a mathematician, he also worked in fields such as fluid dynamics, music theory, and astronomy. He contributed greatly to the field of complex numbers with his formula, his number, and his identity.
So we'll begin with Euler's number, which is often represented by the letter E. Euler's number is like pi in that it's an irrational number, so the decimals go on infinitely. It has many uses in the field of mathematics, like in A-levels, you will learn about its use as the base of natural logarithms. But today we're going to be using it to convert complex numbers in the Cartesian form to the exponential form.
So before we get to Euler's identity, we first have to look at Euler's formula. Now, we've already met the Cartesian form by a complex number, with the real component added to the imaginary component. But we can also use the properties of the number e to represent it in the exponential form, where we also use the imaginary unit I, as well as the length r and angle theta we found earlier. If we take another look at the Argand diagram, we can use trigonometry to find the real and the imaginary components of our number. If you haven't come across trigonometry before, it's an area of maths that relates the side lengths of a triangle to its angles. Now, we can use these representations of x and y and put them into the Cartesian form to find a third form of representing our complex number, the polar form. Now, if we take the exponential and the polar form, we know that because they're representing the same thing, they must be the same as each other. So we can set them equal to each other. And then if we divide through by r, we get Euler's formula. E to the I theta equals cos theta plus I sin theta. I'm sorry if that was slightly fast for you, but the important thing is the end result we have here, as you'll now see.
Now that we have Euler's formula, we can derive Euler's identity, which is a special case of it. You first get to it by having his formula, and you make the angle theta equal to pi, which you can substitute in, pi being 180 degrees, and then we can find the value of cos pi by looking at the graph of cos, and we can find it to be -1, which we can substitute into the formula, and then we can find the sine component, or sine value at pi, which we find as 0. We can then substitute that in, and anything multiplied by 0 is still, anything multiplied by 0 is 0, so we drop the imaginary component and make it 0, And of course, if you add anything, if you add 0 to anything, it's still the same thing. So you can drop that. And this gives us one form of his identity, but it's more popularly seen to be e to the I pi plus 1 equals 0.
So Euler's identity has often been described as an example of mathematical beauty. In fact, Richard Feynman once called it one of the most remarkable, almost outstanding formulas in all of mathematics. And there is a reason for this. The first one being that 3 of the basic arithmetic operations occur exactly once, those being addition, multiplication, and exponentiation. And on top of that, we have 5 identities or numbers that are unique in their own way. The first of those being one that we've already talked about, E, Euler's number. And then we have I, the imaginary unit.
The next one we have is pi, which shows a relationship between the diameter and the circumference of a circle. It's also used when measuring angles. Normally you would say you have 360 degrees for a circle, but you can also say that you have 2 pi radians. So 1 pi radian, which we've got here, is equivalent to 180 degrees.
Then we have 1, which usually you don't think is an important number, but is very important, and it's known as the multiplicative identity, meaning if you multiply anything by 1, you get the original number. Also, 1 is known as the unitary number, which is like based with counting and many geometric things.
And the next number we have is 0, which is the additive identity. So this means that when you add this number to any number, you will always have the original number.
So finally, I'll leave you with a joke. How many mathematicians does it take to change a light bulb minus e to the I pi?